So we're going to do one more example, and that example, let's do one more example, and that's Cl2 reacting with KCl. So I'm going to predict what the reaction is going to happen, who's going to gain electrons, who's going to lose electrons. Step number one was identifying the reactants, and the reactants in our case are chlorine. KCl is an ionic compound. It has K plus one, and it has sorry, this is not, this is KBr. Let me correct that. So KBr is an ionic compound, so it's K plus one and Br minus one. So these are my three species, uh, and someone out of these three is the one that's going to gain electrons, and someone is going to lose electrons. So the next thing is you write down all. Step number two is you open the data booklet and write down all electrode reactions involving these three, whether they're gaining electrons, whether they're losing electrons. So for Cl2, let me open the data booklet. Here's the data booklet. So Cl2 is somewhere at the top over here. So there's Cl2 right next to the cursor, Cl2 gaining 2 electrons to form in equilibrium with 2Cl minus 1, and the value is 1.36 moles. And what else did we have? We had Br minus 1. So Br minus 1 is over here. So you have another reaction in which you have Br2 gaining 2 electrons in equilibrium with 2 Br minus 1. And this value is 1.07 volts. And the third one is for K plus 1. K is K is over here. So for K plus 1 plus 1 electron and in equilibrium with potassium, and the value is minus 2.92 volts. So going back to my board, these are the three electrode reactions that I've written down. And I need to figure out who's going to gain electrons and who's going to lose electrons out of these three. So what's the rule? The rule is that the highest potential one is the one that's going to gain electrons. So in this case, the highest potential one is chlorine. It's going to gain electrons. So this is the one with the highest E naught. It's going to gain electrons. And the other one is, and we also need to ensure that the substance that's gaining electrons, do we have that substance? So if I select this, it's Cl2. It's Cl2 that's going to gain electrons, and I do have Cl2 as one of my reactants. So I've figured out that out of these three, it's Cl2 that's the one that's going to end up gaining electrons. And now I need to figure out who's going to lose electrons. The one that loses electrons is the one with the lowest potential. The lowest potential is this one, potassium. But the thing that's wrong with this is that we don't have, I mean, there is no potassium in our reactants anywhere. So we can't select this because we don't have potassium. So I'm going to remove this. I'm going to cut this out. Take it to the side. Uh, who's the lowest potential now? The lowest potential is this one. It is the one with Br minus 1. It's the one that has the lowest potential, and that's the one that's going to lose electrons. And do we have Br minus 1 with us? If you look at the reactants, you do have Br minus 1. Hence, these two equations are going to be your equations for gaining and losing electrons. And what you're going to do is you're going to sum them up to make an overall equation. And the overall equation is going to be you add you make the number of electrons gained and the number of electrons lost equal. So we have they're already done. Add up the reactants. So the first equation, the reactant is Cl2. In the second equation, if you look at the second equation, the reactant is 2Br minus 1. And you add up the products. The products are, in the first one, the product is 2Cl minus 1. And in the second one, the product is Br2. So this is going to be my overall reaction, and I'll be asked to write the E naught cell, which would be the potential difference between the two, highest potential minus lower potential. So it's going to be 1.36 volts minus 1.07 volts, which comes out to be 0.29 volts, which is not very high, which indicates that the reaction would happen, but it would happen very, very slowly, because the one that's gaining electrons and the one that's losing electrons, the potential difference is not that large. Sarah, is this clear?
Yes.
Achha, so this is predicting redox reactions. Now we're going to do one more thing, which is non-standard electrode potentials. Because these electrode potentials, all the ones that we are studying right now, are calculated under standard. They're calculated under standard conditions. So non-standard electrode non-standard electrode potentials. What does that mean? It means that the reaction is not happening under standard conditions. Uh, Previously, we wrote down these electrodes like sodium ions gaining electrons to form sodium, and the E naught value we calculated that was minus 2.71 volts. Now, the standard conditions are that the ions would have a concentration of 1 mole per decimeter cube, and the temperature of the whole thing would be 298 kelvins, or 25 degrees centigrade. Or and one more thing, which was that if there's any gas, then that gas must be at 1 atmosphere pressure. Now, whatever happened, this equilibrium was established, and let me draw the electrode. Okay, so whatever was going on, it was happening under standard conditions. There was a sodium metallic rod dipped into a sodium ion solution, and sodium was losing electrons. Initially, it was losing electrons, so that it was losing a lot of electrons because it likes to lose electrons, and it was forming all these sodium ions. And eventually, the electrons became so negatively charged. I mean, this electrode became so, it had so many electrons that the positive ions, they started getting attracted to the electrons back again, and that's when a reversible reaction was established. But inherently, this reaction is reversible. And if it's reversible, then all the things about the Chatelier principle, they would apply to it. Which means, and the number one thing is, I mean, what's the Lee-Chatelier principle? The Chatelier principle is that the equilibrium shifts positions if you change the conditions, if you alter the conditions. Now, Le Chatelier principle number one is that if you increase temperature, endothermic reaction is going to be favored. Number two is if you decrease temperature. Let me write temperature. Number two is if you do the opposite, if you decrease temperature, then always exothermic reaction is going to be favored. If you Number three is if you increase pressure, then less gas mole side is favored because you're compressing, so less gas would be produced. Number four, vice versa, is if you decrease pressure, more gas mole side would be is going to be favored. And the last one is about concentration. That if you increase or decrease concentration, equilibrium will try to do the opposite. So if you try to increase or decrease concentration, equilibrium tries to do to do the opposite. So if you try to increase concentration, equilibrium would try to if you try to increase, equilibrium would try to decrease concentration. So this equilibrium is going to shift position. And remember this, that if this equilibrium for some reason shifts in the backward direction, for example, if you've decreased the amount of sodium ions, let's say you've decreased the amount of sodium ions, equilibrium is going to try to make more sodium ions. So the equilibrium would shift backwards. If it shifts backwards, uh, so if equilibrium for any changes that you introduce it shifts backwards, then more electrons are going to be produced. So if this equilibrium, so whatever you do out of all these changes, for example, you decrease the sodium ion concentration, equilibrium would try to make more sodium ions by shifting the reaction in the backward direction. And if it does that, more electrons are going to be produced and your electrode potential would drop because more electrons, equilibrium is shifting backwards, more electrons would be produced on this metallic rod. Then E naught, E decreases. You don't write E naught, uh, you just write E now because naught indicated standard potential or standard conditions. So the E would decrease, would become more negative as more electrons are produced. And similarly, if for any reason the equilibrium does the opposite, it shifts in the forward direction, then sodium ions are going to consume, then these sodium ions over here are going to consume the electrons if it moves in the forward direction. So if it moves in the forward direction, many reasons for it to do that. For example, if you increase concentration of sodium ions, it would try to decrease the concentration of sodium ions by moving in the forward direction. So if it moves in the forward direction, the sodium ions would consume a lot of electrons, and the rod would become electron deficient because the sodium ions would start consuming the electrons if it moves in the forward direction. So the opposite would be, or we can write and vice versa. If equilibrium shifts forward, then the potential would increase. Sara, is this clear? Aisha, is this clear? Abdullah, clear?
Yes, sir.
Yeah, sir.
Achha, so that's one thing. And then, so for example, let's do a few examples. I have a reaction, and we're going to apply Lee-Shatler principle now to those reactions. So there's chlorine gas gaining 2 electrons in equilibrium with Cl minus 1. And the official E naught, the standard under standard conditions, it's 1.36. It's 1.36 volts. So what would happen if I increase pressure? Remember, this is a change that I'm making. If I'm increasing pressure, the standard pressure is 1 atmosphere. I've changed it to 5 atmospheres. So if I increase pressure, the equilibrium would favor less gas mole side. So it's going to favor the less gas mole side, which in this case would be, I mean, this side there's one gas molecule, on the other side this is aqueous, so there is no gas molecule. So which side, I mean, this side is 1 mole of gas, this side there is no gas. So what happens? It's going to shift in the forward direction, less gas mole side. And if it shifts in the forward direction, the new potential is going to be, if it moves in the forward direction, it's going to be greater than 1.36. And it's not going to be a very drastic increase or decrease. It's just going to be a very slight uh, increase in most cases, probably 1.45 or 1.4 volts, but it's going to increase. Okay, Aisha, Sara, is this clear?
Yes.
Yes, sir.
Just similarly, here's another reaction. There is Fe3 plus 1 electron in equilibrium with Fe2 plus, and this is 0.77 volts. So let's say this is 0.5 mole per dm cube, and the Fe2 plus ions are 1.2 mole per dm cube. So compared to standard conditions, what I've done is I've increased Fe2 plus concentration. The equilibrium is going to try and decrease or do the opposite. So it would move in the backward direction. So I've increased Fe2 plus from 1 mole per dm cube to 1.2 mole per dm cube. Equilibrium would try to do the opposite. It's going to try and decrease it. So it's going to favor the backward reaction. Or vice versa, what you could say is that Fe3 plus concentration has been decreased. The equilibrium would try to do the opposite. It's going to try and increase it by making more of it. So if it moves in the backward direction, more electrons are going to be produced, and the new potential is going to be more negative, would be lesser than 0.77 volts. Why? Because the reaction is shifting in the backward direction and more electrons are getting produced. So this is what we call just qualitative analysis of an equation. We're just figuring out whether the potential has increased or whether it has decreased. Then a lot of times you'll be asked to calculate the value of the potential. One example is we have copper 2 plus 2 electrons in equilibrium with copper, and the E naught is 0.34 volts. So it's 0.34 volts. Now, let's now this reaction. This is aqueous. This is solid. And let's say the copper 2 plus concentration has decreased to 0.15 mole per dm cube. So instead of the standard conditions, which is 1 mole per dm cube, it has decreased. So if it decreases, the equilibrium will try to increase it by favoring the backward reaction. And if it favors the backward reaction, more electrons are going to be produced, and your new potential, because more electrons are getting produced, it's going to become more negative. It's going to become lower than the old one. But this is just qualitatively speaking. We want an actual value. We want to know what this new potential is. By just looking at whether it's moving in the backward direction or whether the equilibrium is moving in the forward direction, we have been able to figure out whether it's going to increase or decrease. But now we want an actual value, and the actual value is obtained by the Nernst equation. And this equation is written as E, the new E, is equal to the old E plus 0.059, which is a constant, divided by Z log of oxidized species and its concentration divided by the log of so this is the formula. And the values of this formula are that oxide species is the one that is formed after oxidation. And in the equation, it's always the left side one, the one that's formed after losing electrons. So it's always the left side one. So in any electrode reaction, it's always the left one, or you can call it the reactant. And the reduced species is the one that's formed after reduction. And it's always the right one, this one. So in this equation, it's going to be this one because it's formed after reduction. Copper 2 plus would gain 2 electrons to form copper, so it's formed after reduction. So it's usually the right one, or you can call it the product in the way the equation is written. And Z is the number of electrons. That are involved in this reaction. So in this particular reaction, it's going to be 2 electrons. So I'm going to write the Nernst equation, and I'm going to try and figure out this new potential E, which is going to be E naught, which is this one, the old potential, which is 0.34 volts, plus 0.059, and divide that by Z number of electrons, which are 2, and then log of oxide species. The oxide species is this one, copper 2 plus. The concentration is given as 0.15 divided by the reduced species, which is going to be taken as 1. Because remember that solids always have concentration equal to 1. It's always taken as. So solids will always have a concentration of which would be equal to 1. It's going to be constant. For solids, the concentration does not change. So I'm going to use the Nernst equation and try and figure out. So doing this on my calculator now, it's going to be 0.34 plus 0.059 divided by 2, and then again multiplied by log, and log of 0.15, and I get 0.315 or 0.316 volts. So the E I'm getting is 0.316 volts. This is my new potential instead of 0.34. And we knew that it was going to go backward. We knew that it's going to be lesser than 0.34. Why was it going backward? Because originally it's 1 mole per dm cube, but now it's 0.15, so it has decreased. So you've decreased the concentration, so equilibrium would shift backwards. And that's how you calculate your potential. Sara, is this clear? Aisha, is this clear?
Yes, sir.
Yes, sir.
So let's do another one, which is so you try and do this now. Use the Nernst equation that's already written above. Here's another equation: copper 2 plus in equilibrium with, this should change, in equilibrium with copper 1 plus. Let me find the standard potential, which is so for copper 2 plus. Where's copper? Okay, try and where's copper? Copper, this one. So it's 0.15 volts. So the E naught is 0.15 volts. And your solution, the concentration is 0.02 mole per dm cube for this, and it's 0.08 mole per dm cube for this. So these are obviously non-standard conditions. So find the potential. Sarah, Aisha, can you try and do this and tell me what the answer is? So 0.02 divided by 0.08. What is the answer that you're getting? So the answer that you're getting is 0.13 volts. And does it make sense? If you look over here, you notice that the concentration of copper 1 plus is much higher compared to copper 2 plus. So the equilibrium should shift in the backward direction, according to Lee-Chatelier principle. Why? Because if copper 1 plus concentration is higher, the equilibrium would try to decrease it. So it's going to favor the backward reaction. And if it does that, more electrons are going to be produced, and the potential is going to be, the new potential is going to be lesser than 0.15 volts. And this is what we are getting. We're getting 0.13 volts. So remember how to calculate non-standard electrode potentials. Now, in reactions, for example, there's a reaction going on. And there's another one with Br2. This is 1.36 volts, and this is 1.07 volts. You know that the higher potential gains electrons, so it gains electrons. The lower potential is the one that loses electrons, so it loses electrons. Anyways, this is the reaction that's happening. And the overall reaction, we already did this just now. And the overall reaction is, if you add up the reactants, the first equation, the reactant is Cl2. In the second one, the reactant is 2Br minus 1. And you add up the products. The products in the first one is 2Cl minus 1. And then the second one, the product is Br2. So this is the reaction that's happening. And you might be asked, how do we make this reaction more feasible? Right? Now, the way you can make this more feasible is that if you increase the potential difference, which means the higher potential needs to be even higher. So it would gain electrons even more, and the lower potential should be even lower. So that's how you could make it more feasible. Increase E naught cell somehow. Make higher potential higher. I mean, your electrons are going to flow more, more quickly if the potential difference is greater. Make higher potential higher and the lower potential So how can we make this even higher? Uh, Remember, a higher potential is achieved if the equilibrium shifts in the forward direction. So what you could do is, you could either decrease Cl-1 concentration, because if you do that, the equilibrium would shift in the forward direction, or you could increase pressure. Then less gas mole side would be favored, uh, which in this case is the forward side. So uh, if the reaction goes in the forward direction, the higher potential will become even higher. And the lower potential, we need to make it even lower. We need to make it move in the backward direction. So how can we do that? What we can do is we can increase Br-1 concentration. Or we could decrease Br2 aqueous concentration. Okay, so these are some of the things that can be done so that the reaction overall becomes even more feasible. So whenever you have a complete reaction going on, one gaining electrons, the other one losing electrons, you want to make it gain more electrons, the higher potential one. And so you can think of Le-Chatelier principle and think of the ways in which you could push the reaction even further to the right. So we've thought of that, decrease Cl-1, or you increase pressure. Sarah, is this clear? Aisha, clear?
Yes, sir.
Okay, so these are some of the ways we can make the reaction even more feasible. We'll continue from here in the next class then, okay? Chale, okay. Take care. Allah Hafiz.
Allah Hafiz.